All right. Well, long division looks like this in grade 3 or wherever you did it. 2,748 gets divided by 13. So we set it up this way. And part of the problem with long division, sometimes how it's taught, is it's taught just as a method and you don't really understand what's happening when you first learn it. So when it was taught as a method, they said, just look at the first number. It's a 2. How many 13s are in 2? Well, obviously none. So then you say, well, then look at 27. How many 13s in 27? 2. And they told you then, write the 2 right here. This is important that you write it right there. Now, what we're actually doing at this point helps us understand why the long division algorithm actually works. You're not thinking how many 13s go easily into 2. You're saying how many 13s go easily into 2,000. And it's not really that easy to figure out. But if we think about 2,700, does it make sense that there would be 200 13s? And what the algorithm does is it gets you to think just in smaller numbers. So when I do 2 times 13, it's 26. But really, 200 times 13 is 2,600. So they told you to write the 26 there, but really what you're doing with that 2 there is you're saying 200 times 13 is 2,600. That gets pretty close to 2,748. And then you would need to subtract. So after subtracting, you're left with 148. And we repeat this process again. What gets the closest to this? And now we're thinking in our tens column. Is 10 times 13 or 20 times 13 or 30 times 13, what's the closest to 148? Not going over, of course. Would be 10. Now, the algorithm said, okay, again, just look at the first numbers until you can fit a 13 in there. And the first 2 numbers are 14. How many 13s go into 14? 1. But really what you're looking at is how many 10s go into 148. And 10 times 13. So they usually wrote the 13. I'm going to write the extra 0 there because it really means 10 times 13. And when you subtract, we have 18 left. And now we're in our ones column. So the reason they got you to write it above certain columns wasn't, sometimes they didn't tell you the reason, but the reason was you're actually thinking about 200s, then 10s, and now we're thinking in our ones column. So what number times 13 is close to 18 without going over? 1. And 1 times 13 is 13. Subtract 5, and we would say we have a remainder of 5. If you wanted to take that remainder and say, I would like to figure this out exactly, well, what you've done is you've figured out that 2748 divided by 13 is equal to 211, and there was 5 left over that still needs to be divided by 13, so you could write that as a fraction. That looks like 5 over b. It's supposed to be 5/13. There we go. Nice. And so that's what long division does. Okay? And because it's often taught devoid of meaning, some teachers decide not to teach it because they're like, well, if the students don't understand what's going on, then what's the point of teaching something? However, it's still, the process itself is going to be connected to what we're going to do because we're going to start dividing algebraic expressions. And this same process, repeating the same idea by looking at the biggest numbers and saying, what would make that go away, right? In the first part, what did we get to go away? We got the 2 to go away, right? We got as many numbers as possible to go away when we put 200 there. And this process figures it out all the way through. Okay? So for 4212 divided by 27. You're not going to multiply it by any thousands, because then you'll go over. How many hundreds could we multiply 27 by to still stay under 4,200? If I put 100 in there, I'll get 2,700. If I put 200, I'd get 5,400. 5,400 would be too much. So all I would have is 100 here. 100 times 27 is 2,700, and I subtract. But maybe in third grade you might have been ready for the process of doing things, but maybe you would have had a hard time understanding why it was working. And sometimes that's okay. Okay? Sometimes we learn math that we aren't able to understand yet. Okay? There's definitely some things that you're going to do this year, probably in grade 12, that you're going to learn and you're going to be like, I'm not ready to understand that yet. But what it does is it forms a foundation that maybe the next year in your math class, you're like, oh, that's what that means. All of a sudden you're like, oh, I get SOHCAHTOA. Might have happened in grade 10. Might not have happened for you in grade 9 when you first, or grade 10 when you first learned it. Maybe it happened in grade 11. Maybe it hasn't happened yet. Okay? Now we have 1,512. And we're in the tens column. 10 times 27 would be 270. What's the biggest number that we could put there to get as close to 1,512 as possible? 4? So, yeah, it'll be 4, which will be 40, yeah. 40 would get 4, 8, and 28 would be 108. You might be able to go even higher. 5? No, because that would get you to 1,000 and some. 1,080. 50 would get you to 1,350. 50 would be okay. But 60 would be too much. Okay? So 50, and this is one of the reasons why some argue that long division isn't necessarily the best method. Because you would have to figure out 50, and 50 is 1,350, and if the mental math is getting you here, we run into some problems. Leaves us with 162 left.
So you can do 50 even knowing that it's
Well, if I did 60, if I add another 270 on here, I'll go over, because I've only got 162 left. Okay? And now with 162, 120 plus 42 is 160. It works out perfectly. And we have a remainder of 0, which means that this is perfect. 27 times 156 works perfectly.
Wait, why did we multiply 27 now to get 162?
27 times 6, so that 6 shows up there. So this one's difficult just because the mental math is higher, right? It's your 27 times table, which might not be something you know very well. Often then I suggest do it in 2 parts, right? When I do 5 times 20 and 5 times 7, that'll be 100 plus 35, which is 135. Or when 27 times 6, do 20 times 6 and 7 times 6. 20 times 6 is 120. 7 times 6 is 42. 120 plus 42 makes 162. So this is long division, and what long division requires is that you get the right numbers each time. So when someone suggested 4 here, had you put 4, then long division method wouldn't work because you didn't find the highest number. So there are other division techniques that some argue are better. Okay? So 4212 divided by 27. And I've seen some do it this way. Okay? So you start with whatever number of 27s you think would work out. What would get you close to this? You say, I'd like to take 127s. And 127s is 2,700, leaving me with, right, 1,512. It started off the same as the other one, right? But this is where what Alyssa suggested would still work. So what Alyssa suggested next was 4 27s, or 40 of them. So she said, I'm going to add 40. 40 times 27 was 108. So 40 times 27 would be 1,080. And subtract again. And now we have 432 left. So whereas in the long division, had she chosen a 4, that would have caused problems later on and had to erase everything. But in this technique, you just have to keep finding, and it doesn't matter how long it takes. And here at 437, she'd go, I can see that we can use another 10 of them. Another 10 27s is another 270. And so now I'm left with 162. And so you don't have to get the exact number right away. And maybe at 162, you go, I think I can do 5 27s because I can multiply 5 times 27 pretty good. That's 135. That leaves me with 27. Oh, that gives me one more, 27. I'm down to 0. And in this technique, what did we have? We had a 100, a 40, a 10, a 5, and a 1. If I add those all up, 156. Same answer as before. Some would advocate that this makes more sense to students because you took out 100 of them, now we have 512. I can take out another 40 of them, I can take out another 10, and the stuff that you put on the right-hand side column, it doesn't matter what numbers you started with because it will work out in the end that they'll all add up to 162 no matter where you started. Some people do teach that. I guess I just did. Mr. Lockhart did? Okay.
We taught that other way of factoring that you Oh, okay, sorry, I must have not been there.
Now, so this works, however, for what we're going towards with long division, when we get to algebra, this algorithm works really well for algebra. So we're going to connect this to our algebra. And so we can do that right away, and we'll look at what it looks like. We can answer the question, what does a remainder of 0 mean? We did sort of already. It means that it works perfectly, right? That 4,212 divided by 27 is exactly 156. But when you have a remainder, which we wrote the answer in black here, it means whatever's left still needs to be divided by 13. So 2,748 does not divide perfectly by 13. It still has a little bit left. So now we take this idea of long division and we apply it to algebra. So in our first one, 3x squared minus 4x plus 5, We want to divide that by x minus 2. And so what we did before, and I'm going to switch colors here to help you see it, is in the long division technique, you start looking from left to right, and you look at your biggest numbers, and you said, could I get rid of that? Okay? And you thought, is there a number that I could put that would multiply by what I'm dividing by to get close to this? So we have 3x squared. Is there something you could multiply x minus 2 by to get a 3x squared? What would I multiply x minus 2 by so that my answer has a 3x squared in it? (3x). Okay? And well, we would want exactly 3x squared. So what Tayana says, if I multiply by 3x. So I'm going to put my 3x here because that's my 3x column. Just like when I put my 2, I put it there because it actually meant 200. I'm putting 3x over my 3x column. And if I multiply 3x times x minus 2, what do I get? I get 3x squared perfectly, and 3x times a minus 2 gives me minus 6x. Going back to our long division, can you see that that's exactly the same thing we did in our first step? We looked at the 27 and said, what 100 could we multiply to get 2700, or as close to it as possible? And when we multiply by 200, 200 times 13 is 2600. That got us as close as we could. In algebra, you'll always be able to get that first number exactly. What would I need to multiply x by to get 3x squared? I need to multiply by 3x. And then if we think about what did we do next in our long division? After we got that 2600, we subtracted. So in algebra, we do the same thing. And we have to subtract. Now we put it in brackets because we have to tell ourselves, if we're subtracting all of that, what does that mean? It means 3x squared minus 3x squared. Now that's 0. Yay. But here's where students make mistakes. Negative 4x minus a negative 6x will be plus 2x. So forgetting that you're subtracting all of it is important. You never run into that problem with numbers, right? Did anybody ever think when they were subtracting that maybe they'd subtract the 2's but they'd add 7 and 6? No. Somehow you never make that mistake with numbers. But it can happen quite easily with algebra because you're subtracting the negative 6 as well, which means we're adding. And technically, what do we have here? We have 5 minus 0, which would mean we still have plus 5. You don't have to, because it's just to show that I subtracted and nothing was left. But a lot of people just would write this next. And it's all right if you plus 0 there to help you remind that you still have to subtract that as well. And now we repeat the process. But now, what's our first term? I'm going to switch colors again. Now our first term is 2x. Is there anything you can multiply x minus 2 by to get a 2x? 2. So above your 1's column, you'll write a plus 2. And 2 multiplied by x minus 2 would give us our 2x, which we wanted. And 2 minus 2 is minus 4. And once again, we have to subtract. Of course, this is 0, and you don't need to write that 0. But 5 minus a negative 4 is plus 9. And it seems to happen the most that we make our subtraction error of forgetting the negative 4 in the last step, because you're so close to finished that you'll just go 5 minus 4, 1. Can you see yourself doing that? Yeah, I almost did. You almost did, okay? So we have to remember that that negative sign, and that's why we put it in brackets, applies to the whole thing. So this one has a remainder of 9. And so what this means is that when I divide 3x squared minus 4x plus 5 divided by x minus 2, it's equal to 3x plus 2, but I still have 9 left that would need to be divided by x minus 2. That's left over. It doesn't work out perfectly. If it worked out perfectly, then the remainder would be 0. Yes?
So when you have like the 2, like the purple one, do you multiply? Like, I don't understand.
So this purple 2, right here, it gets multiplied by this whole thing, and that is what went there for your 2x minus 4. Okay? And we did the same thing in long division, right? If I go back to a number, if I say this 5, that 5 got multiplied by the whole 27. But in numbers, you never think, oh, I'm just going to multiply the 5 by the 7. I'm going to forget about the 2. You'd be like, that doesn't make sense, and you never think about it. But you multiplied it by the 2 and the 7, and then that equaled 1350, which went right there, and you subtracted. So we're always doing the same process over and over and over again. So let's do the next one. That's not the button I wanted. Here's the button I wanted. So if we're setting this up with long division, minus x squared minus 2x plus 1, and we're dividing by x plus 1, we look at our first number. I'll color code it again. We did green first last time. Is there something I could multiply x plus 1 by to get a 2x cubed? So again, I'm looking at this x plus 1 right here. That x plus 1, is there something I could multiply that x plus 1 by to get a 2x cubed? 2x squared. So because it's an x squared, I'm going to write it above my x squared column to keep things neat and tidy. And 2x squared multiplied by x plus 1 is 2x cubed, perfect, and 2x squared times the 1 would be plus 2x squared. And I subtract, and our goal is to get rid of the 2x cubes, which we did, and minus x squared minus a 2x squared would leave me with minus 3x squared. And of course here there'd be plus 0 and plus 0, so subtracting that would mean you still have the minus 2x and the plus 1. Switch colors to purple. Now my first term is a minus 3x squared. And we're just going to keep repeating the process until we can't do it anymore. Is there something you could multiply x plus 1 by to get minus 3x squared? Negative 3x. So that'll go over our x column, negative 3x. And we multiply it and we get negative 3x squared minus 3x. Put it in brackets to subtract. And negative 2 minus a negative 3 is, you can write a plus 0 there. And we repeat it one more time. What color should we use after purple? You have choice of dark red, orange, black, or red. Dark orange. So what would we need to multiply x by to get x? 1 plus 1. I don't know how dark that orange is. Medium dark orange. 1 times x would be x. 1 times 1 would be plus 1. Put it in brackets and subtract. And what do we get? 0. Oh, this is exciting. You don't know why this is exciting, but Mr. JR thinks this is very exciting. What does this mean? This means that 2x cubed minus x squared minus 2x plus 1 is equal to, since we divided, right? Like, go back here. We figured out that 4212 was equal to 27 times 156 perfectly. Okay? I'm going to find this exciting. I may get a couple of groans from you, but that's okay. I'm used to it. Minus 3x plus 1 times by, I'm going to write that second. I'm going to write this first. This means that 2x cubed minus x squared minus 2x plus 1 works out perfectly to be x plus 1 times 2x squared minus 3x plus 1. Which is cool, because what have we done to 2x cubed minus x squared minus 2x plus 1? What's another way of calling this? We factored. We factored an x cubed equation. Can you see where this unit is leading? We're going to factor things bigger than we factored before. All right? Okay, this is where I got the groan I was expecting. What's that? Yes, later in the unit you'd say, this question's going to say factor completely. So you go, oh, well, this is x plus 1. And now I'm getting quite good at these. 2x and x, 1 and 1, minus, minus, done. Right? So now, this is considered the easy thing that you know. And we add on factoring cubics, or factoring powers of 4, or factoring anything bigger. So this unit's going to teach us how do we do this. Is that far enough?
Yep. I was doing it on my own and I did that.
How do we do this? Like, we were told to divide first and found out it worked perfectly. How are we going to be able to do that all the way through and factor it? So let's go. Well, they've got an example here. Are you done, Tan? Everything good? Okay. So they've got an example on the next page that walks us through it. Step 1. That's that idea of what would we multiply the x minus 1 by to get an x squared. Okay? Step 2, multiply that through, and then step 3, subtract. And we actually subtracted the 5 as well at the same time. They're doing it a little bit later, but I would have written that 3x plus 5 right away, and then said, what do we need to multiply x by to get a 3x? We need to multiply by 3. Subtract again, and find out that there's a remainder of 8. What does this mean? This means if you tried to write x squared plus 2x plus 5 as x minus 1 times something, the closest you could get would be x plus 3, but it wouldn't quite work. Can you see if you FOIL this out, you would get the x squared. You would get the plus 2x, but you would be a little bit off. You'd be at minus 3 instead of plus 5. We have a remainder of 8 saying, oh, if we added 8 to this, it would work out. It doesn't work perfectly. We have to do something else. We have to add 8 to it to make it work out. So you could think of this as numbers, right? If you did 27 divided by 6, does it work out perfectly? No. What's the closest you could get? 24, which means you'd multiply by 4. 24, there would be a remainder of 3. This means that 27 is equal to 6 times 4. That's as close as we could get. Not quite. We have 3 left over. Right? The difference between long division with regular numbers and long division with algebra is algebra, sometimes the remainder is going to be minus. Sometimes you could subtract. But if you would have done this with your teacher, okay, your teacher would have told you in the past this is wrong. You were like, oh, I want to do 5. 5 times 6 is 30. Oops, I did too much. If I subtract, I went over by 3. Technically, this is not wrong. Because is it still not true that 27 is equal to 6 times 5, and we're off by a little bit? We just need to subtract 3. It means the same thing. But you would have got that one wrong in grade 4 because you went too big. The rule was you couldn't go over. But technically, it means the same thing. In algebra, they're not worried if you go over or not, as long as you're getting as close as possible. So we have some definitions. We say that, do they have all the definitions here? Most of them. They have most of their definitions. So I'll highlight a couple of definitions. Okay? The quotient is your answer. That's your quotient. Okay? We have the remainder, which is what you're left with in the end. Oh, they do have another definition. I've got more highlighters. This part, well, they don't really, but we call that the divisor, so I'll highlight that. And we call this part our polynomial. So all the definitions are there. The part inside we're going to call our polynomial. What we're dividing by, we're calling our divisor. Our answer, when you divide, an answer is a quotient. So since we're dividing, we're going to call our answer the quotient. And sometimes we have a remainder. So let's go to example 1. Now that we've done lots of preamble and practice, I can go back. Back to the colorful everythings. Okay, so I have to push buttons to get everything back for you. Oh, there we go. Doom, doom. There we go.
Where would you rank the unit that we just did? Pretty bad at it.
Okay.
I tried doing the pre.
Well, let's do this first, and then we'll rank units. Okay. Example number 1 introduces an important thing that we have to consider, that we never have to consider for, so number 1, considerations, I'll call them. Considerations. The order. The order matters when you write polynomials and you're doing long division. You never had to worry about this with numbers. So we have 2x cubed plus 5 minus 2x plus 3x squared. We need to write this in order. Okay? That never happens in long division. Let's just divide by. You're like, oh, does anybody ever write, oh, 2,712, I think I would like to write my 7 first, because it means something different, right? But in algebra, these two are equivalent. They don't mean something different, but as far as our work goes, we like to write them in descending order. And one of the things you learned back in grade 9 was descending order is preferred. Well, it comes back to help us in this one. So our first consideration is order matters. We're going to get our second. There's 2 considerations. We don't know our second one yet until we do example 2. And we're dividing by x minus 1. Keep it blue. So the first color we used was green. Is there anything I could multiply x minus 1 by to get 2x cubed? 2x squared. And so we write that above our 2x squared, above our x squared column. And 2x squared times x minus 1 gives us 2x cubed minus 2x squared. Subtract. And of course, that is 0. What am I going to get under here? 5x squared. Excellent. And of course, there would be a bunch of zeros here. So if you're subtracting, you'd still have minus 2x and plus 5. Next color was purple that we used. Wait till we get to the ones where we need 18 colors. No, they don't get that bad. Yeah. But we use 3 colors on this one. We're going to get to some that might use 4 colors or 5 colors. But the next one is the 5x squared. If you could do the green, you're set, because the process is the same just over and over and over again. Right? Now our new number, our new first number is 5x squared. What could I multiply x minus 1 by to get 5x squared? 5x. So we, above our x column, we write plus 5x, and we multiply 5x times x, 5x squared. 5x times a minus 1, minus 5x. Put brackets around it and subtract. Well, this will be 0. Minus 2 minus negative 5 is? Plus 3. Excellent. And there would still be a 0 here, so 5 minus 0 is still plus 5. We went dark orange next. That's our new first term. Oh, dark medium orange, sorry. Medium, no, it was medium dark orange. Whew. MDO. So, what would we need to multiply x by to get 3x? 3. So we play plus 3 here, multiply it through, and we would get 3x minus 3. Subtract, put brackets around it. Ooh, I want my brackets in MDO. And we get a remainder of 8. So we can write up here at the top, remainder 8. What does this mean? If we want to write out what this means that, just have a little bit of space here. I'll write my final thing in back. 2x cubed plus 3x squared minus 2x plus 5. If I want to say it's equal to x minus 1 times something, the closest something that exists, 253, is 2x squared plus 5x plus 3, but it doesn't quite work. Okay? It's off by 8. You have plus 8. If you multiplied this out, do you remember how to multiply something like this out? You'd have arrows from that one, and then you'd have arrows from this one. You have to do the first ones, the first and inside one, the outside ones, the inside ones, the last and inside one, and the last ones. So it spells something like that. Easy to remember. Just like foil is easy to remember. Totally. And if you multiplied all of those out in combined like terms, you would get the 2x cubed. Maybe that's easy to see because that's always your first one. You would get the 3x squared, you would get the minus 2x, and when you did your last ones, minus 1 times 3 is minus 3. You would be off. How much would you be off by? 8. So we add 8 at the end to make it work. But it doesn't work out perfectly. Okay? This is called, what I've written in black here, we have it, is it on the next page? It's on the next page, so we'll talk about it already. This is called the division statement. you're often asked to write the division statement. The division statement is stating what you just discovered. We just discovered that this was equal to this times this, and it didn't quite work. We had to add 8. So the way that we remember our division statement, I'm going to get rid of all of my little check marks and my arrows. I'm going to move this down. In our division statement, we define things. Remember, we called this our polynomial, so I'm going to write a p above it, is equal to, what did we call the x minus 1? The divisor, so that's d. What did we call the 2x squared plus 5x plus 3? The quotient. So it's d times q, dq, and then plus the remainder. So your division statement is p equals dq, because I put it in the middle. I could so I can move it closer. Uh-oh. There we go. No. Yes. Are there any exceptions? You are the exception for this unit. So on your next, on the next page there, they have the division statement, right? Here, the division statement, maybe you write, because if you think about Dairy Queen, it's easy to remember.
Do you always have to do that? When you, like,
No, some questions will just say, like in the example that we just said, it said divide. All you would have needed to do was do your divides and have remainder 8 up at the top, and you would be fine. But when we get to our next example, which I think we should do right away,
for the statement, do you have to write p equals dq plus r, or do you have to write the actual?
you don't have to write the p equals dq plus r. You might do that to help you remember. You have to write the actual answer. So in this one, not this one that we did, but we're going to do this one next. Here, I'll go back. This one that we just did, right? This one just said divide. What I have right here is all you would need to do, because it just said divide. Okay? The next one says write the division statement. Then you're going to need to write out the Dairy Queen statement at the end. Divide it and write the Dairy Queen statement. But for this one, this would have been all that we needed. Okay? Questions for practice on this one are 3 ACD and 5. And if you're a music lover, you can redo C in 3 a second time.